It is my pleasure to introduce our speaker today, Dr. Alyssa Goodman. Dr. Goodman is the Robert Wheeler Wilson Professor of Applied Astronomy at Harvard University, where she has been on the faculty since 1992. Today, Dr. Goodman will be talking about knitting together an amazing new multicolor view of the Milky Way in 3D. Without further ado, I now turn control to Dr. Goodman.
Hi, everybody. I have started with a very odd picture for a talk about the Milky Way, but hopefully many of you in the Northern Hemisphere have gotten to see Comet Neowise. I have not gotten to see it this well. This is a picture from my friend Tom Dame from a few nights ago at Martha's Vineyard. And the reason that I want to show this picture is because I want to think about astronomy as a mostly 2D science. Okay, so if you think about the history of comets, comets appeared on the sky, and there was a huge debate among the ancient Greeks and civilizations even before that about where they really were, how far from Earth they were, and what they meant. And some people, most people, thought that they were harbingers of doom, and that they were somewhere in the realm inside of the moon and some kind of atmospheric phenomenon. And basically, without knowing the distance to the comet, they had it completely wrong. And now we've gotten to the point where we can land spacecraft on comets. So science has advanced, and a 3D understanding of the structure of our solar system was really critical for that. And so what I want to talk about today is a 3D understanding of the structure, not of the solar system, but of the Milky Way. But before I do that, I thought it would be fun to know where everybody is. So you should be able to go to that link at the top of the screen. Just says pollev.com/prediction. And go ahead and click on where you are. It should work now. Let's just give you a few minutes. Let's see, I don't see anything. Ah, thank goodness. Okay, great. It should even work on a phone if some of you are watching this on a phone. Now we have some Northern Canadians up there. Oh, really far north. Wow. Oh, and someone's in England. Isn't this fun? Oh, someone's in Chile. Uh-huh. And oh, what is that? Is that Switzerland? No, it's not Switzerland. Austria. I can't tell who. Is that Joao? I don't know. Anyway, and India. All right, terrific. We're getting there. I'll let this go for another couple minutes. I don't know who the people floating out there above Alaska are. They're amused, or they don't know where they are, or they're somewhere not on Earth. All right, terrific. So this gives us a sense of that this is an audience that would have been pretty difficult to gather in person. So it's fun in a strange way that we're able to do this today. And then let's try the next one. I'd like to know who, whoops, sorry, not this one, who's joined us. So please just choose what you are there on the list. We'll get some. This is not just for fun, but so that I can have an idea of how to adjust my talk to who's here. So we have a lot of graduate students, a fair number of faculty, some postdocs, some undergraduates. I was hoping for a couple of high school students. We got some research staff. I like the just interested, whoever that is. Thank you very much. All right, great. Well, that looks pretty stable. All right, so we got lots of graduate students. We got some undergraduates. Oh, wait, the staff. The postdocs are slow at filling out the poll. The faculty members were also slow. Notice those bars getting bigger and bigger. The graduate students win the prize for filling it out fastest. Okay, great. So we got a lot of graduate students. I'm going to assume some level of a pretty serious astronomy expertise here. Okay, so now here's the next question. Is what do you know about these various things? And I'm not going to explain any of them because that's the idea, is to let you just click on things you think you know something about. I think a lot of you better click on NGVLA or the funding will be a big problem. And when you say knitting, I'm guessing you mean actual knitting with yarn, which interestingly is not going to be, as you might have guessed, what I mean. But okay, this is good. We have a fair number of people who know a lot about the things on the top row. Now I want to know if the 6 people who clicked on Merge Cube were the panelists I showed it to before we started, but I have no way to know that. All right, great. Well, we have a pretty good distribution, and I don't know, 20 of you or so have already heard of the Radcliffe wave. So that's good. We'll get there. That's very good that you have all heard of the next generation VLA. We'll move on and assume that you all know what that is. Okay. So what are all these things, and what do I really want to talk about? I can't possibly in a short talk about all of them. So I'm just going to try to give an idea of why these little images are here, and how this whole story fits together. So it seems like pretty much everybody knew what a spiral galaxy is, but I just want to remind people of the scale, and especially the scale compared to what the next generation VLA could possibly do. So if we look at this galaxy, which is called UGC 12158, which is the favorite Milky Way analog of Mark Reed. Some of you may or may not know that Mark Reed is, if not the expert, one of the experts about measuring the structure of the Milky Way using masers, largely with the VLBA and other VLBI techniques. And he likes this galaxy. It has about the right size bar in the middle. It has these long straight pieces that are analogous to this Radcliffe wave that I'm going to show you later, okay? But we're just going to leave you in suspense about that. And for now, I just want to use this to point out a scale. And so the scale of the disk, of the optical disk anyway, of this galaxy is about 40 kiloparsecs. And so just for reference, if you think about the purported abilities of the NGVLA, you take that 40 kiloparsecs, and that is 0.02 degrees at the distance to that galaxy, 120 megaparsecs. So 1 parsec with that kind of resolution is, sorry, 1 parsec at that distance would be 1.8 milliarc seconds. And if I look at this published advertisement for the next generation VLA, and I draw that line at 1.8 milliarc seconds, you see that that's the only instrument that could go to parsec-like resolution in a relatively nearby galaxy, but not that nearby like this one. And so this next generation VLA could resolve, fine structure inside of molecular clouds, 1 parsec scale structure. So that's interesting. But what's going to be most interesting for later, when I show you what this Radcliffe wave is that it could also easily see sort of 10 or 100 parsec oscillations easily. So could some of these other things out of the plane of the Milky Way. And that's just a hint of what we're going to talk about later. I'll point out, even though I'm supposed to be a big promoter of the GMT, that the GMT actually cannot reach that kind of NG-VLA resolution. So I do hope that project comes to pass in my lifetime. Thank you very much. And I'm much younger than Eric made it sound when he said I've been on the faculty since 1992. I was like 12 in I was a child prodigy. Anyway, okay, so let's move on to knitting. So the kind of knitting I mean, I'm sorry, but doesn't involve actual knitting needles. It involves knitting together information from different sources of information. In particular, the 3 sources that I'm going to talk about today, I'm mostly going to talk about dust, but I'll talk a little bit about gas and stars, because that's how you get to the whole picture. But basically from gas, hopefully lots of you know, a lot of you clicked on spectral line mapping, so you know that you can use the Doppler shift of spectral lines to get the line of sight velocity of gas, and you can get the distribution of gas on the sky. So it gives you a weird 3D position velocity space, right? Which is written here as line of sight velocity plus 2D position. And you can kind of measure gas density, but a lot of molecular line tracers are pretty bad at measuring gas density. What's much better at that is dust. And you might say that you can only get column density from dust. But in fact, you actually can get 3D density if you can also measure distance and 3D positions, which is what I'm going to show you how to do today. And then stars, thanks to astrometry and especially Gaia, you can now get 3D velocities and 3D positions, which turn out to be obviously incredibly useful for endeavors like this one. Now, who is this person at the bottom of the screen so happy this morning? That's Catherine Zucker, who recently got her PhD. And that's me pointing to her to tell you something very important, which is that so much of what I'm going to talk about today was done and is being done by Catherine Zucker and a lot of collaborators of Catherine's and mine, most notably Doug Finkbeiner, who was Catherine's other PhD advisor in addition to me, and Joao Alves, who was kind of also Catherine's PhD advisor. And basically we're all collaborators and we all work for Catherine. And there's a bunch of other people involved, mostly notably former students of Doug Finkbeiner, and you'll see all their names in a bit. But really, so Catherine is on this as a panelist. And so if you want to ask her questions in the chat as we go along, She can type answers as or in the question and answer, wherever you want to type. She can type questions, type answers, because she's not talking. So if I was going to give you an entire talk about like Catherine's whole thesis and what this whole project is about, I would show you all of the things on this screen. But instead, I'm really going to focus mostly on 3D dust mapping, but just emphasize that this so-called knitting requires really more dimensions of information. We need the velocity from the gas, which comes largely from radio astronomy, as well as the density distribution. And I'm not going to talk about these things, these very long, skinny molecular clouds that we found several years ago that turn out to also be good tracers of the structure of the galaxy. But you'll see in a bit that you can click on some diagrams I'm going to show you to get a lot more information. This suggestive figure down here, I will show you. For now, though, what I'm going to show you is something Catherine and I wired up this morning so that you could have a kind of souvenir of this talk. So this extraordinarily complicated looking diagram is actually from a proposal, from an ADAP proposal that we just submitted to NASA, showing how all of this knitting work is going to be done. And if I can't show you even just what was on the other slide in the time we have, I certainly can't show you what's on this slide. But what I can show you is kind of how this works. So a lot of groundwork has already been done. So I'm going to show you in a few minutes how you connect distances and velocity, how you connect 3D dust mapping with position, velocity cubes in a demo that Catherine Zucker did in Perseus. And then I'm going to show you a bunch of other things. But before I do that, let me just point out that the multicolor aspect of this is something I wanted to say first. So these surveys, it doesn't matter what they are, I'll show you in a minute, but come from radio wavelengths. And then the stellar catalogs that we use to do all this come from a range from pretty long wavelength infrared, WISE, glimpse, to shorter optical wavelengths to try to quantify the colors of stars that turn out to be important later. And for some particularly special regions in the galaxy, we actually are also using X-ray data as tracers of points of feedback, like the centers of supernova explosion, things like that. So anyway, to get back, oh, I almost forgot the most important thing. I'm not going to talk about my favorite software project today, which is Glue, which is this, hopefully you'll ask me in the questions, is the key piece of software that we actually use to connect all of these data sets and visualize and understand what's going on. And you'll see sort of some screenshots from that in a little while. But in order to really analyze data from many different regimes and in many different 2D, 3D formats, catalogs, et cetera, all together, that's our favorite way to do it these days. So to go back to what I was saying, if you click on any one of these boxes, so let's click on this one, okay, you get to the paper and the figure that explains what that part of the chart means, okay? So, you know, if you want to know what all these data sets are, you can click on one of them. If you want to, you know, get a 3D dust map of your favorite region, you can go here and read about how to do that. But we don't have time to do all that. So I just want to let you know that this is available, and it'll give you an idea of what actually is done in order to knit all of this data together. And so again, the stuff that's in green, sorry for anybody who's colorblind, but the stuff that's in green has already been done. The stuff that's in this sort of pale yellow is all the data sets that go into this Brutus machinery, which is what takes the incredible number of stellar catalogs and makes new catalogs, merged catalogs out of them that can give you information about the spectral energy distribution of stars, which gives you information about their color. And then we use the colors of the stars that are changed by the intervening dust to make a 3D dust map. And I'm going to give you a much clearer graphical explanation of that in a minute, but that's what's in this box. And then all of this is being shared publicly and ultimately leads to a 3D position plus 1D velocity model of the Milky Way, which will be shared online and be available in 3D augmented reality. And hopefully at the end, if you can see the tiny picture of me on your screen, I'm holding up a special toy that I will show you how you get to see the 4D information. And just to remind you, this tinyurl.com/Milky Way knitting, if you're really curious, jot that down. Maybe Catherine can put it in the chat so you can refer to it later to go see that diagram. So let me move on now. All right, so let's start with our highlighted special feature of today, which is the Radcliffe wave. And what is the Radcliffe wave? I think about 20 of you already know, but these slides here are actually from a press conference that we gave about this at the AAS earlier this year when we could still travel back to Hawaii. And so I'm just gonna leave this here for a minute so that you can read this long list of names of people who were really critical to this work, which was the paper was led by João Alves, who may have been that person that looked like he was in Austria for this talk. Anyway, so what is this? Let's proceed. Let's remember that the thing that's kind of bluish here in the background is a cartoon model of the Milky Way that we see all the time, and that it's extremely hard to see structures inside of the Milky Way because I think, as just about everybody on this webinar knows, we're inside the Milky Way. But these red dots here are not a cartoon. These red dots are actual data that show you the structure of a gigantic gas and dust feature in the Milky Way that we didn't know was there. So here's a sort of animation using a worldwide telescope to show you where this thing is and how big it is. So every red dot there is the 3D position of a big chunk of a star forming region whose distance has been incredibly accurately measured by the technique I'm going to describe in a couple of minutes, okay? But just to put this in context for you, the sun is actually incredibly close to this feature, and it's kind of astonishing that we didn't know that it was there. Okay, so let's wait just a minute. There's the sun. And you notice it has this kind of sinusoidal shape from the side. And it turns out that from the top, it's incredibly straight. It doesn't look like a spiral arm so much. It looks like one of those long straight sections of an arm that I showed you in Mark Reed's favorite galaxy. Okay, so I'm sorry these numbers are in light years here because, like I said, these particular slides were from a press conference. So I trust you can divide by 3. Okay, so it's actually 2.7 kiloparsecs long, and it oscillates about 160 parsecs, 170 out of the plane, which is astonishing. And it has more than 3 million times the mass of the sun. And so, other than looking really weird, there's sort of 2 triumphs here. One is that in order to do this, you actually have to be able to measure distances incredibly accurately. And that's a huge part of what Catherine worked on in her thesis. And the distance accuracy, as I'll show you in an animation in a second, is now at something like 5%. And we have new data that I can't show you today, new results actually from other people who we're going to be collaborating with, that are more like 1% distances. So it gets even better than what I'm going to show you today. But anyway, and then the other one is the thing that I've been focusing on so far, which is that it has this incredibly bizarre shape. But before I go on, especially since I'm sure there's a lot of VLBA people on the call, they're going, well, you know, I thought masers are the best way to measure distances. And they certainly are to regions where there are masers. Okay, but this technique relies on just dust, just on the changes of stellar light colors by dust. And so that can be done anywhere in the galaxy, and masers can only be observed where there are masers in H2 regions that are usually associated with massive star-forming regions. So if you look at the region that we looked at on the sky where the Radcliffe wave turns out to be, and you compare maser distances, okay, with the 3D dust distances, we were really surprised when we saw how good this is. Okay, so this is a 1-to-1 line. I don't think anybody's going to argue that there's a problem with the accuracy of these distances. So how did the Radcliffe wave get discovered from just better data and better statistics? This is how, okay? Because you sort of cross a critical threshold in distance uncertainty that lets you sort things out. So this is just a schematic cartoon, and the distance before, the distance uncertainties from the sun, so if I put this on here, you know that you can only measure the distance along these lines of sight from the sun, were, you know, about as big as those red lines. So, you know, they were like 30% in a lot of cases. And, you know, maybe you could imagine that you saw some structures there, but people wouldn't try really to do that. But then if you improve the distance uncertainty dramatically, okay, you start to see, you know, these 5% distances, very clear structures. And so you say to yourself, like, well, how did this happen? One is this technique that I keep promising to describe to you that I'll show you in a minute. Another one is constraining the 3D dust mapping technique with Gaia distances to individual stars or to groups of stars. The third one is the glue software I mentioned before. And the fourth one is worldwide telescope for the purpose of 3D visualization and understanding what's going on. And you'll note here that, you know, the little asterisks are interesting to this audience. So I'll let you know that this is 2 million CPU hours, thanks Harvard, 800 million stars, thank you ESA, and then NASA and JWST, and the NSF pay for GLUE, and the NSF and the AAS are currently supporting Worldwide Telescope. So finally, how do you do 3D extinction mapping? Let's say you have a telescope, hopefully better than that one, and imagine you have a star out here. And again, this is a cartoon, right? Okay, so let's say that star is that greenish color, and then I put a bunch of dust, 3D distribution of dust out there in space. So that particular star will have its color reddened, right, as the starlight passes through the cloud. And if you do that for a whole bunch of stars, and just to remind you, that kind of reddening is just like the reddening that you have in the sunset. And so if you do that for a whole bunch of stars, and we'll just assume that they're all the same color, which of course we know that they're not actually the same color, or for the sake of illustration, imagine they were the same color. They pass through different amounts of dust, right? And they all turn out to be different colors when you observe them. So if you have some way to know the intrinsic colors of these stars, and bonus, if you also know or can deduce the distances, you can then infer statistically the three-dimensional distribution of dust that would give you the observed two-dimensional distribution of colors. And boy, am I making that sound easier than it is. Okay, so it's 10 years of research, mostly in Doug Finkbinder's group, to make that possible. Okay, but all you have to know for right now, because we don't have much time, is that you can infer the distance to the stuff, to the gray stuff, from the effect that it has on starlight. Okay? And then if you throw in Gaia, and Gaia lets you know the distances to individual stars, then you don't have to solve for those distances as part of your statistical solution. And you can use that as a prior, essentially, for those of you who know what I mean. And you can get incredibly lovely maps of the distribution of dust near the sun, which is what this is. And you can actually already see in this map, you can see this big, long, straight thing, which turns out to be the Radcliffe wave. So what Catherine did was actually optimize the analysis so that instead of trying to measure distances kind of with roughly similar accuracy to everywhere near the sun, to kind of take enough of the data at once to get super accurate distances to individual star forming regions. And what you see on the screen now is just a screenshot from this GLUE software that I'd be happy to show you or talk about at the end, that lets you combine different models of spiral arms, maser data, dust data, gas data, all kinds of things, and try to understand what's going on. And so when we first plotted the positions of these clouds, we thought, you know, maybe this is some sort of spur off of the spiral arm. If you look here in this little part of the screenshot, this series of red dots turns out to be the Radcliffe wave. And you'll notice that the cartoon arm kind of goes like this. And we thought maybe it's some sort of wispy spur. I'll just tell you, long story short, it turns out to be that it actually is the spiral arm, okay? But let me first say, why didn't we find this before? Okay, if you look at the Radcliffe wave on the sky, again, this is GLUE and Worldwide Telescope, doesn't look like a particularly impressive pattern, okay? You really have to understand what this looks like in 3D. And I'm gonna show you an interactive of what it looks like in 3D in just a second. But just to remind you of the history of all this, Gaia is relatively recent. You know, DR2 is 2018. GLUE has only been around for less than a decade. The 3D dust mapping technique, as I mentioned, also less than, but almost a decade. And then we have, you know, Worldwide Telescope and Maser VLBI going all the way back, you know, say 20 years. So it's really kind of the technological and data science improvements that have let this become possible. So this is actually the figure from the Nature paper that shows you a top-down view of the arrangement of clouds, an end-on view of this wave, and then a side-on view right here. And I'm going to do something dangerous here, and I'm going to jump out of the presentation and open a browser window and show you a website that I'm going to show you in a minute anyway. So it's called tinyurl.com/radwave. If you go there, it says you can surf the Radcliffe wave. You can see about all the collaborators. If I click on visuals here, then an interactive figure, again, created using GLUE, made by Catherine, will load. And so this is the same figure, the same three figures you just saw from the Nature paper. Here's the side view, the end-on view, and the top-down view. But the difference here is that this is an interactive figure. So I can zoom around and I can move things and show you what's going on. And so if let me turn off clouds that are not part of the Radcliffe wave for just a minute, and let me show you what happens if I turn on a model of a damped sine wave for that distribution of points. It's kind of incredible. So this is a this is not forced in any way, okay? And if you look at this from the top, okay, whoops, sorry, you can see that it's mostly this very long straight thing. From the side, it's a sine wave, and from the end, it's very tiny. And if you look at the previous model of the local arm, it looks like that, okay? And if you see, let me turn off the data here for the Radcliffe wave, and let me turn off the fit, you can see that the data were very sparse. And Tom Dame and Mark Reed were trying to fit a log normal spiral arm through all of that, and they did a pretty okay job. But if you have a lot more data, okay, you can see that locally, that's actually not a very good fit to the arm at all. So it turns out, given the Maser and the dust distance agreement, that everybody now agrees that this just is the local arm locally. And if you're interested in what the other stuff is, a lot of that is actually the Sagittarius arm over here. And then there's some interesting features that you can see the names of the clouds here that are sort of off of the Radcliffe wave. But anyway, like I said, we have new data that I'm not going to show you today that lets you also see very interesting interactions near the sun that have to do with feedback and may also be related to the Radcliffe wave. And you can try asking me about that, and I can try answering, but I might not be able to today. Okay. So just to summarize, you know, why do we care? Oh, I forgot to show you something very important. If Joao is listening, he will hurt me if I don't show you this. I left on the figure, did I? Yes, okay. There's this famous thing called Gould's belt. Okay, let me turn off the other things. Okay, Gould's belt was what was thought to explain the distribution of molecular clouds near the sun. And if you look, if you kind of tilt this end on and you only see this section of the wave, you do see that there's this kind of diagonal structure in projection. And if you turn it this way and you include a few of these blue things, you could almost imagine that there's this ring here, okay? But in fact, the points that are part of what was thought to be this belt are actually part of this much longer wave-like structure. So if we go back here, now I've told you, right? So it's the demise of Gould's belt. The local arm is not shaped like we thought. It's straight from the top down and has a giant wave in it, okay? We don't know what caused it. We're working on some analysis that may suggest it's a collision. We're having a meeting here, hopefully in person in the spring, with people who want to help figure out what this is. And we don't know whether other parts of the Milky Way have this structure. This I showed you is very close by, so it's easy to see, relatively easy. We don't know what this means in terms of the star forming history locally. And one interesting thing, again, for this sort of NGVLA world is if you had edge-on galaxies imaged at super high resolution, could you see any evidence of these oscillations in individual clouds that you could map out? So I'm quite curious about that. But anyway, if you want to know more about that, you can go to this Radcliffe wave website. But for now, I just want to tell you about the last couple of things here. And in particular, I want to say, what about if you try to combine velocity information with this? And I'm just going to talk for maybe 3 or 4 more minutes, I hope. And so I'll just say that if you throw in spectral line data, okay, so now you don't just have position, position, position space, but you also have position, position, velocity space. That gives you the line of sight gas velocity in addition to knowing the distance to all of this gray stuff. And Catherine, again, did an experimental pilot project on this a couple of years ago where she looked at just Perseus, where there's been a huge amount of analysis, and in particular, there's this infamous little rotating map that you see here, which is a 3D looking map of Perseus, but in fact, that is position, position, velocity space, okay? So if you took that map and you pretended it was a cube and then you viewed it from the front and the top and the end, you would get these 3 panels. You would see it on the plane of the sky like this, you would see a position velocity diagram like this from one side, and then you would see a position velocity diagram like that from the end. But what Catherine was able to do is find the distance to each one of these colored blobs that you see up here. And so this plot down here is, again, right ascension along the x-axis, but actual distance, okay? Not velocity, but actual distance on the y-axis. You notice, interestingly, there's actually a gradient in distance that trends with velocity. And so this plot over here is actually velocity knitted to distance, right? This velocity is a function of effectively distance. And so this is what we mean by knitting. And so this is for a teeny region where we've done it, but we now actually believe that we have enough data and enough computing to do that using the wide array of data that you see here and all of the techniques and the previous results to do that for the entire Milky Way. And so soon, this will not be a cartoon. This will actually be all a data-driven 3D version of the Milky Way. So the very last thing I want to do is I want to show you, we're going to have a big problem displaying. I already showed you some interactive figures, but now I want to show you what this thing is in my hand. Okay, so this thing is called a merge cube. And I think that we're going to have to take 3D technology from gaming and from education and from movies into science for real. Certainly not just for outreach. It's great for outreach, but I think we also have to do it for understanding what's going on, because GLUE and Worldwide Telescope are pretty great, but we really have to add more capability for interacting with 3D data. And so I'm just about to show you something on the screen. Hang on one second. I've almost got it going. Okay, this is my iPhone that I'm holding in my hand. Okay, and I'm hopefully about to show you the screen of my iPhone. Can somebody who can turn their sound on make noise and tell me if you're seeing this properly?
Yes.
Yeah, good.
Thank you. Okay, so I am holding the solar system in my hand, and the solar system is moving. This is my kitchen, by the way, in the background. And if you'd like, I can leave the solar system there. I can remove the cube. See, you can see me over here. Here's the cube. And I can walk around the solar system and investigate things and zoom in and zoom out by physically moving the phone. And again, so with the combination of something I can move with one hand and something I can move with the other hand, I can do some pretty spectacular things. And you'll notice that on the screen, there's also a little icon that looks like goggles. And that's because you can also use this with, let me stop sharing my screen, with augmented reality goggles like I'm holding up now. A lot of people don't necessarily want to do that, but if you do, it frees up your hands to say, use a keyboard and interact statistically with your data at the same time that you manipulate it in 3D, which I think is actually necessary for us to accomplish the kind of analysis and get the kind of understanding that we want. So that was what I wanted to say to you today, and I'm happy to take questions now. Thanks. As I stopped sharing my screen, sorry. Here you go.
That's wonderful, Alyssa. Thank you so much. We had a few questions from the audience that I'd like to run by you now.
Sure.
One of which is questions about the Radcliffe wave and asking if you've explored it in relation to the corrugation structure seen in the old H1 surveys.
Yes, yes, we have tried to do that. And so those structures are not in the same place as where the Radcliffe wave are, and they have a smaller amplitude, actually, in the most case, than the Radcliffe wave does itself. They came up when we were doing this Milky Way Bones project, and we were looking toward the inner galaxy. So this structure is toward the outer galaxy from the sun. Toward the inner galaxy, there's this structure called Nessie, which seems to be directly in the plane of the galaxy. And it's odd that it is. And people brought up, well, there were these sort of 50 parsec corrugations in H1. Why is Nessie, this dust cloud, directly in the geometric plane of the galaxy? And that itself is a very interesting question. But one of the things that brought up was we were hanging out in Crete, again, when we could travel last fall, Catherine and I, with Tom Dame and Mark Heyer and Charlie Latta and people like that. And they were all asking about what this has to do with kind of the flaring of the galaxy. And so let me see if I can, let me stop sharing my screen. And if we're particularly interested in this question, I can show you something else. If I open a different, much more elaborate presentation, I can show you kind of in the context of the shape of the galaxy, how this all works. So hang on one second. Desktop, yes. Here, these are from a much longer colloquium about this. And so I really hate how Zoom messes up all your menus. Okay, so in other words, here's a spherical bulge of a galaxy. Here's a bar of a galaxy. And then, oh, sorry, this is not exactly where I wanted. I wanted to go to, hang on one second. This is what I wanted. So that was that. Here we go. Okay, so using those pieces I just showed you, allegedly the Milky Way has a bulge, a thin disk, a thick disk, and some sort of flaring or warping. And so the interesting thing is that if you look at this terrible cartoon, toward the outside, the scale height of the galaxy is expected to be much bigger. And in Tom Damon and Mark Heyer's review from the annual reviews, they have this lovely plot that summarizes the scale height of CO and does show the galaxy getting thicker and thicker as it goes out. And it's interesting that the Radcliffe wave is about the same amplitude as what the maximum CO extent was known to be for that radius. And so how to fit this kind of flaring story, the warping story, the slightly different stories that you see in CO, H1, and dust together is definitely part of the knitting quest. So good question. Thanks.
Great. Another question was, could you comment on the approximate sizes of the clouds and go in a little more about the observability of similar structures in nearby galaxies?
Sure. So the clouds themselves in the Radcliffe wave are famous clouds. And so if I share my screen again, I can, let me share the whole desktop. If I go back to the browser, so each one of those red dots, if I just zoom in here and hover over them, you'll notice that here's Orion, here's Orion Lamb. These were all like pieces of Orion. And so like this whole region, just know that from here to here is 2.7 kiloparsecs from one end to the other. And the individual clouds that are in there are tens to hundreds of parsecs in size. It depends what you call a cloud. Eric is the world's expert on dendrogramming things, and we have to decide how fine we want the structure of what we're going to call a cloud to be. But if you call the Orion giant like the cloud a cloud, it's kind of this whole thing that I'm hovering over here, and that's a couple hundred parsecs in extent at least. And so they're pretty big. And so what's really important is that if I turn on this, what happened? I zoomed in too far. If I turn on this side view, right, this amplitude here is about 170 parsecs of the wave. And so this is possible with the VLA or ALMA now. And so we're sort of looking into, how much confusion you would have because in other words, they're all the clouds, right? But because we know the distances to these things and the velocity of things, we actually can separate them. And so you could potentially separate the red from the blue in an edge-on galaxy, but it would be pretty hard. And so ideally what you want is some sort of tilted galaxy with some piece that's sticking out, and you want to be able to find it. And since there's really no precedent for this, we don't know how to do that. And so one of the students who's working in our group and also with Lars Hernquist and the broader AREPO collaboration right now is Gus Bean. And he's one of the people who's made these models of collisions. And those models might show us telltale things where things happen to clouds, where they stick out of the bigger cloud distribution a little bit, and that might make it easier. But right now, in other words, the resolution is there to do this. It's not the size of the cloud and everything isn't the problem. The confusion is the problem.
All right. I'm actually going to try to merge a couple questions here. One was, can you tell us more about feedback history and the Radcliffe wave? And another one, which may be related, is, are there inhomogeneities in the ionized gas that follow the structure as well? So like pulsar dispersion measure. You can
the pulsar dispersion measure one, I don't know. We should look. I'm not sure that we would be able to disentangle the distances well enough, but we might, so that's a good question. In terms of H2 regions and stuff, that's more related to the first part of the question about feedback. And so it turns out that there's a very smart postdoc at the CFA now named Shmuel Bialy, and he came to me in the fall and he asked about, he wanted to really kind of understand in a cloud like Perseus, how would the phases of the interstellar medium really interact and how could we map this out? So we started looking with Catherine again at H1 data that he had from the GALFA survey. And we found pretty quickly, we rediscovered actually a big bubble in H1 that had been seen at much lower resolution that Perseus is at the edge of. So there's another famous bubble that's kind of in the Perseus molecular cloud. So there's bubbles on all scales. So like B5, which is a little region at the end of Perseus, has a tiny little hole in it. And then just here, I'll use my fingers instead of data. So if the B5 hole is that big, okay, the H2 region that Barnard knew about is about this big. And the shell that Shmuel and Catherine and I saw, quote unquote, again, with Joao Alves and other people, is like this big, like the whole screen, okay? But then it turns out that there's another shell that's like bigger than the screen, okay? And we saw those first in position velocity data, but then with this new data from a survey that uses Gaussian processes to measure the 3D dust distances, you can actually see those structures in real 3D density space. And so what we're trying to do now is disentangle or re-entangle, I guess you should say, do this knitting of the PPV and 3D real space to kind of get a good sense of what these bubbles are. But to give you some idea, in the inner, if you take a 400 parsec radius from the sun, another very smart person at the CFA, Mike Foley, who's a young graduate student now, he's been looking for a census of these bubbles, looking at the 3D data, and he thinks he sees up to 40 bubbles of different sizes within just that 800 parsec diameter sphere. And so we're looking at Gaia to try to figure out what stars' motions are in the region, and we already have some hint from Gaia that the Radcliffe wave is oscillating, and there's some hint that some of these spheres and shells are kind of centered on the Radcliffe wave, kind of on the clouds, you know, that go along, but it's not crystal clear yet. So, you know, ask me next summer. Mm-hmm. Catherine, do you have anything to add about that?
You mean about the oscillations and Gaia data, the stellar velocity?
And the interaction between that and feedback.
So we think that, so one thing I will note is that feedback is fundamentally affecting the shape of the Radcliffe wave, like you said, on small scales. But we have definitely ruled out it affecting the structure on large scales. And so there's sort of feedback on multiple scales. But we think—
That's right. The oscillation is not itself caused by feedback. That we can tell so far. Right. Yeah.
Okay. Can you talk a little bit about how far out in distance you can do good distance mapping? And can you even extend to other galaxies like LMC or Andromeda?
Okay. Let me put that figure back up with all the data, and then I'll say a little bit, and Catherine might want to say more. Hang on a second. Okay, wait, that's the wrong presentation. Hang on one second. Where do we go? Here we are. Here. Okay. So now if you look at this in a little bit more detail, okay, right now, the distance uncertainty in the Radcliffe wave specialized data set is, you know, of order, I don't know, 10 parsecs or less, okay? 10 parsecs at best. The distance uncertainty, if you use this different technique that doesn't analyze along individual lines of sight, but it analyzes using kind of a Gaussian kernel, Gaussian process it's called, but in 3D itself, that's this new map that has like almost 1 parsec, between 1 and 2 parsec resolution, but only right now for the inner 400 parsecs from the sun, okay? But what this shows you is that if you include all of these things in the yellow boxes, and you have a tremendous stellar catalog so that you know the 3D positions and colors of all these stars. And actually, Catherine, I can click on one of these, right? Hang on, let me do this. Whoops, you know, let me go back to the thing where I can click it and show you. There's a beautiful graphic that Catherine and Josh Spiegel made that gives you some idea of just how many stars we're talking about. So if I go here, you can still see my screen, I hope. And then, Catherine, which box do I click on to get that beautiful thing?
The wind map.
The catalog?
The Halo star catalog above at the very top. Are you talking about?
Yeah, that one. Yeah, okay, great. And so this is let me see if I can, sorry. It's the reason I look like such an incompetent person is because for those of you who have not done this on Zoom, Zoom blocks all big parts of your screen and you can't see what's going on. So anyway, so if I go here and I turn on these controls, this is a visualization of an analysis of stars led by Josh and Catherine, Josh Spiegel, where what you're seeing here is I can choose density, velocity, metallicity, and then I can choose this for different distance bins. So you get some idea of the richness of the Gaia data, and Zoom is slowing it down just a little bit. But anyway, you could play with this and you can see what happens if you use just one survey at a time as opposed to many surveys. And I don't have time to keep playing with this, but I highly recommend this link, okay? And that was from from the box that says Halo Star Catalog up here, okay, Spiegel et al. 2020. And importantly, that lets you go farther out of the plane and into the plane. So in other words, out of the plane is always easier because there's less confusion and less extinction. But in the plane is difficult. And this is going to actually let you go. This was this 3D dust map optimized for the galactic plane in the plane. And so with all of this, okay, I would say the goal, I would say realistically 4 kiloparsecs from the sun, but Catherine's going to say like 6 to 8 kiloparsecs from the sun. What are you going to say, Catherine?
Yeah, I would say 6. And so the challenge is always that in order to do 3D dust mapping, you have to see stars behind clouds. And so right now we're only sensitive out to a few kiloparsecs, but we're currently, you see all the data sets on in the yellow boxes, things like GLIMPS and WISE. Those are longer wavelength infrared surveys. And so they allow us to see more stars behind clouds than if you're just using optical. And so we're incorporating those and hoping to get out to the 6 kiloparsecs in the next year or two.
And this, for those of you who are interested in statistics, this Brutus code is really something to behold in that there's a sort of joint analysis of all of these data and the distances and the metallicities and the ages and the colors and everything that comes out all at once. And so Eric, you would really appreciate the way it's done in particular. And just to give Eric a little plug here, the way that the clouds are going to be connected to the dust is by using a catalog that was based on an idea that Eric brought to astronomy when he was at the CFA of using dendrograms, applying dendrograms to spectral line catalogs. And so that has already been done in a paper by Tom Rice a few years ago now. There's a existing catalog for CO. And so those clouds will be used as anchors to get distances for them from this big catalog.
Okay, excellent.
And that goes all the way to the other side of the galaxy, but I don't believe it on the other side of the galaxy.
I had a couple more questions for you.
Sure.
One is just a bit, could you say a little bit about what you would sort of infer about normal versus dark and dark matter distribution in the Milky Way from your work on Redcliffe Wave and other?
Yeah, so, you know, people like Lisa Randall really love the idea that there's dark matter hidden in the disk of the Milky Way. And until we have a good model of what a collision looks like and what the oscillations resulting from that would look like, it's really hard to say whether you need extra mass than what we know about. But we're getting astonishingly close, actually. Just yesterday, we were looking at some work that, again, Catherine's been supervising, being done by an undergraduate named Alan too, that uses the Gaia 3D motions. And I should just mention that the people at the American Museum of Natural History, and particularly Jackie Faraday, is involved in this project too. And we're using something called open space to kind of visualize all these 3D motions, because it's really hard to go back and forth between the kind of statistical proof or not proof of what's going on and the data. And I can't stress enough how important it is to see kind of where are the outliers, where are the patterns coming from. And it's hard to tell, you know, whether you have a real oscillation that you can believe. And so you need some combination of analyzing the data, visualizing the data, and then a model of what the kind of magnitude and shape of that oscillation would be. And it's that last part that's the hardest. And Gus Bean and a lot of other people are working on that. So I'm gonna say the jury's out on missing mass being responsible for the oscillation until we know more about that there is an oscillation. The one good news is that Orion is at one of the crests and is moving at almost zero velocity. And so it's kind of a good idea that the wave should be turning around where Orion is, and that we knew that that was true actually already before this recent Gaia analysis. So it's promising that it's actually oscillating.
All right, I'm going to ask one last question, but I note
Sure.
that there still are 10 more questions, so I encourage anyone who hasn't had their questions answered to feel free to get in touch with Alyssa and Catherine through the links that she's provided through this talk. But the one question to close on is, where can we learn more about the merge cube and other applications for?
Thank you for asking. Okay, so if you remember here, oh, I can't, sorry. Zoom also takes over the lovely touch bar of my screen, so I can't see my slides and jump around to them. But if you remember this screenshot here, okay, this is a screenshot from the wonderful Glue software, which by the way, is being put entirely into Jupyter Notebook and Jupyter Lab so that you can run this on the web. And the thought is to actually take this, in the same way Worldwide Telescope is a plugin in that lower left corner, to actually have what you just saw be a plugin where you use this cube to just control whatever 3D data you have open in Glue or OpenSpace or Worldwide Telescope. We're not quite sure yet. So we actually need some developers who want to make that happen. So we have a couple of developers who are sort of working on it in the background, but it's very peripheral to what they're doing. So in all seriousness, if somebody wants to do that, there is an API, there is Glue, there is money for collaboration from the NSF. We really just need a person who's quite interested in doing that. So soon is the answer to your question, but it depends on personnel. It should be possible.
Well, excellent. Thank you very much, Alyssa, and thanks to everybody who attending. Normally, this is the point where we would say, let's thank our speaker one more time, but without anybody unmuted, we can't do that. So thank you a lot, and Joan Roble has been posting the link to the schedule for next week and past talks into the chat, so you should have access to it there. And otherwise, we look forward to seeing you all next week. Thank you.
And I will put these slides on my website right now. Bye.